Good morning, everyone. Today's subject is thermal engineering. My name is T. Dharma Teja, and roll number is 209518034. Today's topic is the design and analysis of a water cooling system in a New Yorkless and segmented amateur axial in wheel motor for electric vehicles. Introduction. Various new energy vehicles, electric vehicles have been developed and deeply investigated due to the increasing environmental and energy concerns in recent years. 1 to 3. An internal combustion engine is replaced with an electric motors and a batteries in electric vehicles. More Moreover, compared with the centralized driving systems with single or dual electrical motors, a distributed driving system such as an in-wheel driving system have been generated due to the advantages in exhaust emission, noise, power of performance, and simplified powertrain structure requirements on the electrical motor. Thus, significantly differ from that of a traditional internal combustion engine. And in a wheel motor for an electrical vehicle general requires high power and torque density, which leads to the significant heat generation. 78 magnetic properties of a motor are highly sensitive to temperature and significantly affected by generated heat from the motor itself when running under a low voltage high current load, as such as a vehicle's accelerating and climbing situations. The in-wheel motor generates extreme heat and the possession of challenge the heat dissipation. Furthermore, due to the reconstruction of the electric vehicle with the distributed driving system, particularly its powertrain structure, the requirements of compactness, that high weight on the wheel motor excavates at the heat dissipations problem. Therefore, cooling of a high wheel motor is vital importance. Thermal conjugative models. Due to the new structures of the motor, the FEM method instead of commonly used thermal resistance network method was adopted in this study. Both the fluid parts and solid structure of the motor were modeled in analysis fluent to the built and a conjugative thermal analysis model where the hydraulic and thermal performance of the motor can be studied. To boost the simulations, only key parts of the motor were considered in the simulation, particularly the stators that do not bridge thermal reactions between the coils and fins and have limited fluency on thermal balance, thermal thermal interaction between the coils and flames, limited fluency and thermal balance were ignored. The heat generated from the stators was added to the coils and calculated as an equivalent heating rate. The forced air convection in the study was also ignored due to its relative small influence compared with that of cooling water. Small features on the motor were implemented in order to improve the mesh quality. The end covers were also omitted as they are not of corner in the study and have little influence on the temperature distribution of the temperature sensitivity coils. The fluid domain was considered for the thermal conjugative modeling and meshed with the highly quality meshes. Figure 4 shows us the meshes of complication fluid dynamics CFD model of the motor with a 6-path layout. A water cooled in a wheel motor. A pure electric passenger vehicle characterized by distributing the driving, lightweighting, and artificial intelligent driving has been developed. The vehicle has two separated in-wheel driving systems as shown for the developed in-wheel motor is particularly developed for the in-wheel driving system, and the motor has smaller dimensions, 230 into 130 and the weight of the 13 kgs, and the table and list of the main parameters of the in-wheel motor. Moreover, newly designed gear reduces the bridges in the wheel motor and its corresponding wheels, as shown in the figure. We can see in the wheel driving system supported by newly designed activity suspensions. The motor gear reduces the brake and suspensions are integrated into the wheel and shows the assembly of the in-wheel motor. Shows the sections view of the motor. The main structure of the motor is designed based on the conceptual design and design targets of the motor of the developed electrical vehicles. This part of the work is partly introduced in the literature, and the water cooling system and the structure are based on the design of the motor. Results and discussion. Uh, the figure 5a and figure 5b shows the fluid pressure distribution and the flow velocity of the water path. The figure 5c and figure 5d displays the temperature distribution of the water path and the motor with the 9-path layout under the normal working conditions. The hydraulic pressure reduces gradually from the inlet to the outlet, and the abyss pressure drop can be found in the small holes and anti-degree functions of the holes. Moreover, the isolated heat and outlet areas on the shell cylinder surfaces had uniform pressure. The transition area had a gradual pressure transition. The 90 degrees junction significantly increased the pressure resistance and strongly lead to the turbulent flow. The fluid velocity field well matched the pressure distribution along the each copper coil evenly generates heat temperature pressure uh, distribution differs due to the continual heat transmission by cooling water. The low temperature at the inlet and a high temperature at the outlet were predicted by the simulation. As water flowing through the path from the inlet to the outlet, its temperature rises and cooling effect reduces. Furthermore, the highest temperature is one of the coils near the outlet and the closeness to the motor center axis. All the simulations with other water parts layouts presented similar pressure and temperature distribution trends. Conclusion: the newly designed Vision wheel motor can well satisfy conflict recurrence on the thermal balance and a compliance for the electric vehicles with the distributed driving system. Water path layout in the visual importance regarding the hydraulic pressure and the temperature, which have combined influence on the thermal balance and the motor efficiency and the performance. The developed thermal conjugative model and accurately simulate the thermal performance of the motor. A detailed hydraulic pressure and temperature distribution can be presented by the model, and the small falling area leads to the high driving pressure and high flow speed, which increases energy consumption on the water pump while improves the cooling effect. However, the manufacturability than a general efficiency of the motor should be balanced when the designing of the cooling path layout. The 6-path and 3-path layouts have to the potential as the optional motor cooling system layouts. Under the extreme work conditions of both the layouts present a good cooling effect. A prototype motor with the 6-path layout was successfully built and tested on the experimental rig. and the prototype presents as a good cooling effect which matches the numerical simulations well. Thank you for giving this wonderful opportunity to share my views. Thank you, Ananda.